Okay, the phenomenon of weight reduction of a spinning wheel by R weight. Eric Lathwaite he did a famous demonstration which was so frightening to the people who watched it that they thought that he was in league with the evil powers, and they froze him out. His old friends wouldn't talk to him anymore and so on. He died finally working in the United States on a railgun satellite launcher. But this video is in existence. You can look it up, and he holds a 40-pound gyro with one hand, apparently not even straining, over his head, and the thing spinning, of course. And everyone knew that that was impossible, so there had to be, he had to be gone into devil worship or something. And then this experiment has been reproduced in Australia. And there in Australia, they stand on a scale to illustrate the fact that there's weight loss in case of a spinning wheel. But theoretically, there was no verification of this until, as far as I know, until Waite came along with this article. He explains that there has to be weight loss this way. If you have a simple wheel at the end of a pole gyro, and you have it steadily precessing, there's a formula that tells you how fast it has to spin in relation to its moment of inertia and the length of the handle and so on. And I think he has it right here. Yeah, here it is, formula 4. V sub p is the linear velocity as it goes around in a circle. And m is the mass, g is the force of acceleration due to gravity, L is the length of the handle, I is the moment of inertia, and omega is the angular velocity of the thing. All right, so from that you usually derive formula 1, namely the mgh, that's the gravitational potential energy, is equal to F sub v, which is the average force. He's going to lift the handle straight up vertically, and at the same time he's going to apply an impulse force to it sideways to make it precess faster. All right, well then you get this formula. If V sub p is the original precession velocity, not an angular velocity, though a linear velocity, so we can get kinetic energy. And then he goes up to 2 times that velocity. The difference has to be positive. If the average upward force is positive, h is positive because that's the height that's increasing as he lifts it up, and mgh is how much potential energy it gains as he lifts the handle. Now, I should mention that it turns out that if a gyroscope is, if its precession angular velocity increases, then it starts to nutate. It goes up, and then it goes down, and then it goes up, and then it goes down. But if as it goes up, once this impulse force is applied to double the velocity, linear velocity as it goes around, if you lift the handle as the thing nutates upward, it then falls back into only precession mode where it's not nutating anymore. That's the thing he's using. So therefore, this equation holds, and if you divide by h, which is positive, you get mg is equal to F sub V plus a positive quantity. So therefore, mg has to be greater than F sub V, which means that there has to occur weight loss. I guess I'll ask, are there any questions at this point? This is.
Yeah, I mean, what does he base this derivation on? I mean,
Well, it's potential energy and kinetic energy. It's a conservation of energy argument.
huh, oh, it's just based on conservation of energy.
Yeah, see, here's the, if you lift of height h, it's mgh is increase in potential energy. And then the kinetic energy, if the thing goes around in a circle, and then if you double the velocity that goes around, you get this difference here as the other part of the energy. Because when you lift the handle in synchronous with the thing nutating upwards, it then begins to precess. So that's about it. There definitely has to be weight loss for a spinning wheel. But then he goes on to calculate how much, and then he tests it with some equipment, a load cell hooked to a computer, he said. And since I'm not an equipment man, I don't really follow a lot of this. Here's the weight gain illustrated.
You mean loss?
Yeah, loss, pardon me. Actually, thank you for bringing that point up. It turns out that there are two types of masses, gravitational mass and inertial mass. And gravitational mass is supposedly equal to inertial mass. However, we'll see that that's apparently not true. Even the GPS guy, Ron Hatt, said that wasn't true, but in this case, what if the inertial mass increased, but the gravitational mass did not stayed the same? Then Newton used to talk about inertial force, which he visualized as the inertial part of the object pushing against the applied active force. And so then if that's true, and gravitational mass doesn't increase or decrease, stays the same, then the inertial mass, if it increases, the object will appear to be lighter because there's more inertial force pushing upwards against the gravitational force. So there's
oh, okay, got it.
Okay, so
But what about the downward direction since it's spinning?
I don't follow that question.
Well, if it's spinning, then there's it's spinning up and it's spinning down. If it's
But
I'm not. All right, don't let me interrupt. I think I understood that point that you were making there. Yeah.
So now, why would the gravitational mass not change, but the inertial mass change? Well, there's two theories of gravity that I'll mention. First, general relativity, curved space-time. It's not clear to me at all that gravitational mass can change just because something's spinning. I mean, the elevator experiment would seem to refute that. But I don't want to go into that, though, because I don't believe in general relativity. The other one is that Martin Spears has an electrostatic theory of gravity, which would indicate that the gravitational mass is not a function of whether you're spinning or not. It has to do with Coulomb's law of electrostatics. So and if you, as I say, if you take the gravitational mass to be the same, the inertial mass will kick up because of the fact that the thing as a whole You know, you can look at different particles and then integrate. But the thing as a whole will gain inertial mass and hence apparently lose weight.
Why does it, would you explain again why it loses weight as the inertial mass increases, and what causes the inertial mass to increase?
Well, the inertial mass increases because of this energy thing here. That is to say, the inertial mass is, according to Newton, is the force that pushes upward against the force of gravity and keeps the thing from accelerating almost to infinity.
Right.
And what was the other half of your question?
So you explained why inertial mass increases because of the energy considerations.
Yes.
And why does the weight decrease as the inertial mass increases?
According to Newton, inertial mass is not what he talked about. It was inertial force. That is to say, the inertia pushes upward against the gravity to keep it from only accelerating at g, 9.806 meters per second squared. But if the inertia were to increase, then the upward push of inertia would increase. And since the gravitational force downward stays the same, the thing apparently becomes lighter.
Okay.
So the fact that if it's a peer-reviewed journal, which, okay, let's just going on the assumption that we think it is.
Yeah.
And this looks to be kind of like extending the controversy. And I've heard about this Eric Lathwaite, I think is his name. Is that how you pronounce it?
Yeah.
And supposedly there were at one time videos on YouTube or on the internet, but I don't know whether they're available anymore.
Oh, yeah. Well, at least they were a couple of years ago, last time I looked. Yeah. He's, and there's one in Australia, which is even better than his. Now, here's a paper that got me started on my Neo-Newtonian theory, which we're talking about today. Frequency dependence of a rotor's free-falling acceleration and inequality of inertial and gravitational masses. All right, now what happens is that it's airtight. It has two, what he calls aviation rotors in a spinning, one in one direction, one in the other at various frequencies in hertz. Hertz is along here. So as you can see, it's sort of a mixed bag, but the measured in gal is 1 centimeter per second squared. See, the negative would mean that it was getting lighter, which means then that the inertial mass is getting larger. So here we see that gradually as you increase in hertz, you get a lot of vibration, but it steadily decreases in weight as the thing spins higher and higher. As I said, there are two rotors, coaxial rotors, and one spinning one way, the other way, but the same angular velocity, scalar angular velocity, absolute. So I decided to fit this data to, and then, you can also extend it in the negative direction because it doesn't matter whether you're spinning right or left. So it actually extends out here and you get 112 points if 2 times 56. There's 56 here, plus 1 extra point at 0, 0. So it's 113 points in data. And these rotors are in a vacuum. They evacuated the air from the container and then dropped it so that the rotor axes were parallel to the ground. And measure it with some electronic equipment very accurately.
The axis of rotation is horizontal.
Yeah, there's 2 rotors, identical rotors, but one is spinning and to the right and the other to the left.
All right, and the axis of the spinning axis is parallel to the surface of the Earth, so it's
Yeah.
horizontal.
Yeah, it's
Okay.
parallel, it's perpendicular to gravity. Okay, I should have caught that. Okay, well, all right, so what we see here is something different than what Waite did, because Waite had a pivot. You know, he moved the pivot up and down or vertically, but he still had precession and nutation. Here, the rotors are just falling. So why would they fall at a different rate? Well, apparently because they're getting lighter, which means that the inertial mass is getting bigger as on the average. You know, although now why would there be all this stochastic looking data though? Well, think of a top loading washing machine like the one I got here in my apartment. If the thing's in the dry cycle, as it starts out at 0 RPM and begins to speed up, since the load is usually not perfectly distributed, all of a sudden it goes bang, 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 like that. You know, as you pass a certain frequency, which is resonant, which resonant phenomena occurring. So I think that's what's happening here. That's why I fitted it to a quadratic, the least square fit to a quadratic. Okay, well, enough said about that. So that's the data concern. What about the theory?
You would think that the Russians would have noticed. You're familiar with these Tupolev airplanes that the Russians have, where they have counter-rotating propellers. Are you familiar with that?
Yeah. They tried that in this country, but they worked fine except for one thing. They were loud, really loud.
Yeah, but you would have think they would have discovered stuff like this when they testing and.
This looks like a big deal, but we're talking about 1 centimeter per second squared. I mean, this is tiny.
Oh, okay.
All right, now we're coming to the theory behind it. A revised comparison of our Neo-Newtonian mechanical percent inertial mass increase with a percent relativistic mass increase at various high velocity of a small circling mass or something like that. I forget.
Who is this by?
Me, I wrote this.
Okay.
Okay, so here's, we examine a case study of Professor Respik Uzbamatov, consisting of an object with center of mass rotating about a fixed point in a circle with constant angular acceleration in the light of our Newtonian mechanics, which involves variable increasing inertial mass. We calculate using Professor Uzbamatov's case study parameters, both the Newtonian percent mass gain and relativistic percent mass gain at various high velocities occurring in this situation, show that the relativistic effect is completely negligible compared to the Neo-Newtonian effect. Okay, now a word about Neo-Newtonian mechanics. It turns out that if you allow the inertial mass to change in Newtonian mechanics, so you still have F equals ma, but the mass is now a generalized mass, the mass which we've seen in this falling rotor thing, for example. So you still have F equals ma and everything goes pretty much as before, but you have to allow the inertial mass to increase in certain cases, like a gyroscope, for example. So what would this inertial mass increase depend upon? Well, you wouldn't want it to depend on position because, who cares where it is? And you wouldn't want it dependent on velocity because, we don't really know the velocity of the Earth around the sun, or is it the velocity You just don't know. So you don't want to be a velocity effect. So you'd have to make an acceleration and a vector effect and a time derivative of it, the acceleration vector effect. And so if you work out, you know, based on the experiments and so on, if you work it out, the percent mass increase is equal to the acceleration magnitude squared times the time derivative of the acceleration vector is called the jerk vector, J-E-R-K. But times the square of the magnitude of the jerk vector times the fourth power of the cosine of the angle between the two vectors. So in other words, if the two vectors, the acceleration and the time derivative of the jerk vector are perpendicular, as in the case of a steady spinning wheel, then there's no effect. But if there's braking or acceleration of the wheel as it's spinning up or down, then you do get an effect. So let's see. All right, now we based on that, we calculate all the various parameters. Here we've got something spinning in a circle, accelerating slightly as it goes around. The angular velocity as it goes around the circle increases at 7 radians per second squared constantly. And that is to say, there's no, this time derivative is a constant. Now you might say, hey, wait a minute, wait, then its derivative will vanish and therefore there shouldn't be any effect. Well, no, because we're talking about vectors here, not scalars. All right, the initial angular velocity is 10 radians per second, WIN, so that's sort of irrelevant. Okay, so we compute the accelerations and the time derivative acceleration vectors and dot product them. Here's this constant that I got from the falling rotor data, fitting the falling rotor data to my theory. A squared, J squared, cosine alpha to the fourth. That's all it is. So if you plug all this stuff in, what do you get? You get this expression here. Here is the K. It went inside because derived K comes after D probably. And so you have the angular acceleration to the fourth power times K times the radius of the circle to the fourth power times the time derivative, double time derivative of omega, which is 0 because d omega is a constant, plus 2 times omega cubed. Omega cubed is the angular velocity at any particular time, and the whole thing to the fourth power divided by double time derivative, which goes to 0. This was 0 here too, omega squared and so on and whatnot. Notice that the angle theta is gone above since the situation is symmetric with respect to the circular motion. There's no angle that's particularly important. Okay, now the value of K has been computed to be about 1.786 times 10 to the minus 13, small. However, if we substitute into this, simplifying, substituting, simplifying, multiplying times 100 to get the percent instead of just the fraction. Okay, now we calculate the percent inertial mass gains over 100% for various run times. And if there's 0 time, this is essentially 0. If there's 10 to the 4th seconds that's run, you get a point, about 1/3 of a percent in mass increase. And all the way down here, if it's 5 times 10 to the 4th seconds elapsed, you get about 8.4% increase. All right, now we compute the relativistic mass in percent mass increase. And get this thing, see the relativistic increase at these velocities is about 0. But the inertial, the generalized mass gain goes up to 8.4%. So we can see this is a much more powerful effect than is in special relativity.
So is this formula that you came up with, is it accurate? Is this?
Well, you know, how do you get data to check this stuff? It's not easy to do. I mean, anybody in this country who works in academia and tried to do something like this would be fired, tenure and all. So that's a difficult question to answer, but it seems to be all right, giving roughly the right answer. But you know, we at least fitted it to Dimitriev's data, so it does give Dimitriev's data. But you'd like to know if it gave some other people's data. Well, how are you supposed to find out if anybody does an experiment, they get fired?
But the strange thing is that in these papers and your own paper, I think, Danny, you appear to be using classical mechanics. I mean, on the face of it.
Well, yeah, F equals ma, except that m is variable.
Yeah, but I mean that equation 1 in the very first paper which you gave seemed to be the basis of everything. I mean, that was just a classical equation, but you know, the experimental results obviously differed. Maybe from.
I don't quite follow you, Ian. I'm sorry.
Sorry, you don't what?
I don't follow you. What paper are you referring to?
No, I'm just a little confused. I mean, you know, I know you're saying that the variable mass principle, and this is, you know, the mass is getting lighter, is at variance with what we'd all been told.
Growing. It's apparently the weight is less, but the inertial mass is growing.
Yeah. And I can understand how, you know, experiments could be done that could perhaps substantiate that. But the sort of analysis that appears to, I'm not sure about your own one here now because you've gone into a lot of detail, but certainly the first paper, it didn't seem to be at variance with classical dynamics as far as I could see. I don't know what the big fundamental theoretical.
Weight reduction of a spinning wheel, is that the one you're referring to?
I think I was, yes.
Yeah. Yeah. Well, this is you know, this mechanics that I've thought of comes down to classical mechanics in almost all cases. You know, this is, and we've still kept F equals ma. So, you know, if you know things look like a lot like the same, yes, this according to classical mechanics, this effect, this Neo-Newtonian generalized mass effect, could be taken to be an energy effect in classical mechanics. But the trouble is that doesn't allow you to compute things very easily. So you have to change the math to make the computation easier. That's basically my approach.
But by the way, is there some parallel with that German writer that you've talked about? You know, the book Gooch, is that the way you pronounce his name?
Gucci, yeah.
Yeah, you know, where he's talking also, as far as I recall, about Neo-Newtonian mechanics, where I think the mass is also variable.
No, his mass is not variable.
Let me ask you a question that you've already answered in you know, our private conversations, but I think it might be worth hearing it. In Wheeler and Thorne's book, Gravitation, he claims that the so-called relativistic effects, I prefer to call them high-speed effects, are a function of velocity, and that they are definitely not a function of acceleration.
That's right.
Okay, and you came back with an interesting reply.
Yeah, You can't really compare oranges and apples, but in some sense you have to here. Because this thing going around in a circle is accelerating at an angular velocity of 7 radians per second squared. It gradually increases in speed linearly as far as the angular velocity is concerned. So it's accelerating as far as considering it a point particle. It has a centrifugal acceleration, but it also has, since it's the angular velocity is increasing, it has another acceleration. And since it has an acceleration vector and a time derivative acceleration vector, a jerk vector, both of which are not zero and they're not normal to each other, there has to be an effect that can be correlated with the velocity, even though it's actually an acceleration and a jerk effect. But to compare them, since relativistic mass increases a velocity effect, you have to do something like I've done here. And so I just wanted to give you some idea of how these things play out in a special example.
Okay.
Now, we're talking about here about a book called Newtonian Electrodynamics, which I'll hold up to the screen here. This book has 2 experiments which seem to completely be unbelievably far off from what's predicted by relativistic electrodynamics. The first one is if you take a fine aluminum wire, say, or copper, and which is it has a circular cross section, and you charge a capacitor bank with 80 kilovolts of voltage, and then all of a sudden you let this thing go along the wire. The wire breaks up into little tiny fragments. Here's the fragments, a close-up view. Here's even a more close-up view. And here's a microscopic view where you can see that it's actually a fracture. It's not a molten thing. The thing didn't melt down. So how to explain this? Well, they use Ampere's circuit law, his original law, and talk about current elements, which are cubes in the wire, and if one is directly ahead of the other, they repel each other according to Ampere's law. So therefore, according to Ampere's law, the wire should try to get longer and longer, but it can't do that very much because it's not a rubber band or something, it's a wire. So what happens is that the thing breaks up into all these little tiny fragments. And this is called the exploding wire phenomenon. And how would that be explained by Neo-Newtonian mechanics? Well, when you let this capacitor bank go, the electrons, which are very light, of course, very massless, almost, they all of a sudden they're accelerated almost to the speed of light. And so they gain a tremendous amount of inertial mass because the jerk vector and the acceleration vector are collinear here. And so this would explain why the lattice in the wire snaps, because you've got, instead of ping pong balls going up and down the wire, you've got bowling balls all of a sudden.
Dennis, I have a question about the exploding wire. Viewers might misinterpret. You talked about the electron being accelerated to near light speed.
Yeah.
So someone might think that, okay, the effect can easily be explained by relativistic increase in mass.
Uh-huh. Well, you see,
But
it's like maybe a tenth of the speed of light, but if you plug that in, you have to really be almost to the speed of light for there to be any real effect. The preceding paper where I showed the difference between my theory and relativistic mass gain. Relativistic mass gain, unless you're almost at the speed of light, you can basically ignore. And this, and in the wires, you don't actually get up to the speed of light. There's collisions with the lattice, but you get tremendous acceleration, and also it's nonlinear, so you get a tremendous jerk vector. And so I might also mention that they talk about relativistic mass gain, but at SLAC, they basically ruled that out. They claim that, no, that's an illusion. And they have a linear accelerator where it's a straight shot right down the line. But in CERN, they go in a figure 8, I believe. So they've got all these strange rotational effects that they have to calculate. And they all seem to hang together, but are they correct? The SLAC people would say no. It's like they would claim, I think, that it's like when the federal government investigates, say, the Department of X. The Department of X, the people all get together, they make a list of the questions of any question they might be conceivably be asked. And then they make up their story so that no one will be found to contradict another one, and then there would be trouble. And so I think this finding at SLAC indicates that you can't really believe all that stuff. It hangs together like the story of the Department X when they're quizzed in Congress. All their stories line up. There's no discrepancies, even though the whole thing is a fabrication. But they made sure that they wouldn't be caught saying one thing by one guy and a different thing by another guy. All right, now there's another one called the Electrodynamic Impulse Pendulum. And here's the capacitor bank, and here's the thing that feeds into the thing. This is basically a much bigger experiment, but it's based on the Ampere hairpin experiment. There's a slight spark gap, so they're not connected mechanically. And there's a slide, a cardboard slide, which measures how far the pendulum goes when to the left when the capacitor bank is let go. Now there's if this was classical electrodynamical effect, the Lorentz force law would pull the thing to the left. Here you can see you have tiny threads holding it up in the air. But if Ampere's law would indicate that the hairpin part of it, the pendulum part, is not pulled, but it's pushed. And this can be tested, and they find out, yes, it's pushed, it's not pulled. All right, but that's not the most interesting part. The most interesting part is that if you measure how far the impulse given to the hairpin part on the left here, you find that the energy the mechanical energy is 2,000 times greater than the energy, the electrostatic energy in the capacitor bank. 2,000 now, a multiplicative factor of 2,000. So let me bring this up a little bit so you can read it. So they here again, they use 80 kilovolts in the capacitor bank. And so how is this explained by Ampere's law? Well, it's the same thing. If two current elements are one behind the other as far as velocity is concerned, then they repel each other. So this would repel the part on the right, would repel the part on the left as the spark jumps, spark gap at E, and then you can watch it, you can measure how far it goes and use classical mechanics. So, but what about my Neo-Newtonian theory? Well, here again, you have all these bowling balls type electrons crashing into the far end of the hairpin, the pendulum, and they give it they send it flying. And then they give up a lot of their energy, then they come back and complete the circuit. So here again, it seems that these two experiments are explainable somehow based on inertial mass gain, which we've seen has been, it's no doubt that it happens. I mean, it's been experimentally detected. So that's, there's other problems with Lorentz law versus the Ampere law. The forces are not always in the same direction, for example. But this is the two that my Newtonian mechanics might help explain. Any questions on this?
What, where did this diagram, is this from the book?
Yeah, the book, Newtonian Electrodynamics. I'll hold it up.
Okay, now,
It's
I've read, I don't recall this diagram, but I made a copy of one of these. Is this Greneau?
Greneau or Greneau, I don't know how you pronounce it.
Neil Greneau.
It's, Peter Greneau, but his son is Neil, who was his assistant.
Yeah, that to me is confusing. So
Yeah.
I one time years ago made a copy of one of the books that they wrote, and I'm not sure whether it's the same as this one because I don't recall seeing this diagram. Okay, so my question, Carl Herring, do you know who Carl Herring is?
I've heard of the Herring submarine experiment or something like that.
Well, he did a lot of experiments that are somewhat similar to this in the 1920 time frame, where he did a lot of experiments with Ampere's law and was basically disagreeing with classical electromagnetics. But it didn't seem that a lot of his stuff was followed up. He did a lot of early work on Ampere's, on these forces, Ampere's forces and that sort of thing. Okay, so I just wanted to, so this is kind of a follow-on to.
Well, it's more of a follow-on to Ampere because this is basically Ampere's hairpin here, the pendulum.
Right.
But yes, they do mention Herring in the book, as I just pointed out.
I have a copy. I made a photocopy of one of the books. I can't remember whether it's the book that you're referring to or not. And
well, they have several. They had Neumann Electrodynamics or something like that.
Yeah, I'm not sure which one I read. It was so many years ago. I can't really recall. All right. Sorry for interrupting.
That's all right. And now, but what, but even at slack, you might say, well, all right, it's a straight shot and there's just, there's no rotational effects. But how do you know that the percent mass gain, the Newtonian percent mass gain is 0? Well, all you have to do is to show that the jerk vector vanishes, and that would be the case since you're taking the inner product of the jerk vector and the acceleration vector. All you have to show is that the jerk vector gets very small. And that would be the case if the acceleration vector were nearly constant. We know its direction is constant, but what if its magnitude was roughly constant, or at least near the measuring device? It was almost constant. Then you wouldn't get any Neo-Newtonian mass gain, because 0 times anything is 0. The inner product of the 0 vector with any vector is a 0 vector, it's 0. Yeah, so I can't help but wonder if all these rotational effects I think up and everything are sort of like Department X getting together and making sure that all the facts that can be verified they're in line with, and or at least how they interpret them and so on.
Well, that's resistance to establishment resistance to change.
Well, but it's the way they operate now. They're not interested in truth. They're interested in getting their contract renewed, their grant renewed.
Right. So I at one time read, and we're talking 25, 30 years ago, read these papers about the exploding wires. And I have to admit that I really didn't understand what they were talking about.
Well, you run this huge current through a fine wire and the thing busts up into pieces.
Yeah, but I mean, we know that. That's the principle of a fuse in an electric circuit.
Yeah. No, what was the quantity, by the way, that increased by a factor of 2000? Was that the voltage?
No, it's the energy.
Yeah. The energy.
I'm kind of confused here because I see that K is a Rogowski coil. Yeah. And you have a spark gap. So this is not a DC current that you're sending through this thing. It's an AC current. Yeah,
because it's like a pendulum. You start out, it swings wide and then less and less and finally stops. Only this.
Yeah, but it's like a wireless transmitter. I mean, it's not a DC current. It's an AC current, like in a wireless transmitter.
Right. If it was a DC, there would be no acceleration, and hence the Newtonian effect would vanish.
Right. So if you see there, you got a capacitor, and in series with it, you have this K, which is a Rogowski coil. I'm assuming that's a big inductance.
Well, I don't know. What it does is it measures the current back and forth until the current dies out.
Oh, so that's measuring the current. That's not actually, but you still have an inductance here. This hairpin is an inductance, and you have a capacitor.
Well, it's part of it. It's because of the two spark gaps. It's part of a circuit that can, however, move.
Right. The fact is, when you have a spark gap, that means you're going to have an AC oscillation.
Yeah. Well, yeah. And that's measured by the Rogowski thing.
Okay. I thought that was some kind of part of the, okay. So that's just a measuring, current measuring coil.
Yeah, let me check and make sure on it. It might be voltage.
I think you're right about that. I couldn't understand what Rogowski coil was. All right, that makes sense. It doesn't show it's connected to anything. Okay, but you still, presumably you have some kind of a spark is going to be generated when there's,
Yeah, at the points E, there's one up
Right.
here and one here.
so, you've got basically an inductive circuit and a capacitor. So, and it's kind of hard to say. I mean, I'd like, one would like to see what this diagram of the measured current looks like.
Yeah. Oh, it looks like a oscillation with a rapid decay.
Right, okay, that's just like in a wireless transmitter, okay.
Yeah. And it lasts for just a fraction of a second,
It's probably heavily damped.
But the thing is, this smells a lot like free energy.
Yeah, yeah, well, I guess that's why they don't want to talk about it. That's why it's forbidden.
Yeah, because and if you look at my Newtonian theory, if you define kinetic energy as 1/2 mv squared, where m is generalized mass, then you usually get the same as without with just classical mechanics. But in a case like this, you get a tremendous increase in mass and hence a tremendous increase in kinetic energy. So it looks like in certain cases, you do get free energy. That's not a popular view, of course.
Well, as I was mentioning before, many years ago, when I first I got involved with Ivor Cat and
Yeah.
criticisms. And one of the things that I did was I went through the literature to look at a lot of things that were regarded as contradictions or things that didn't add up in electromagnetic theory. And these Grignot experiments was one of the things. The Carl Herring experiments, he did a bunch of experiments where he claimed that they were not explainable and according to the current theory. And there doesn't appear to be a lot of follow-up to what he did. And then Grignot, which is what we're talking about here, did these experiments on the exploding wires and these pendulum experiments. And they claim that the accepted electromagnetic theory doesn't agree with these, but is not consistent with these.
Yeah. Well, they calculate everything right down to all the effects and everything. And they show mathematically that it's the Lorentz force may actually exist, but it's so small in comparison with the ampere forces that who knows? But so this need not necessarily rule out Lorentz force. It's just there's another force that completely trumps it.
So this hasn't really been followed up. Basically, that's the bottom line.
Well, no, because it's so far out. I mean, if you don't like to teach, if you're teaching classical electrodynamics and someone comes in and says you're off by a factor of 2,000,
that's pretty significant.
So they froze him out. He left MIT finally and went to Northeastern, where he finished up his career. Okay, and one last paper, again by Dimitrov. He shoots a ball bearing at a steel plate. Sometimes he does it downwards, up and down, and other times he does it sideways.
So he's doing it with gravity and perpendicular to gravity.
Yeah. All right, and you should get the same result, the same impact over rebound velocity, or rebound over impact. You should get the same result whether you're with gravity or gravity is sideways, but you don't. Why not? Well, I have 4 appendices, one for each of these 4 points. Okay, so the answer seems to be this: because it's the inner product of the jerk vector and the acceleration vector, In the case of up and down, the acceleration vector is either on the way down, the acceleration vector is added to by the gravitational vector. And as it rebounds, you have the opposite effect. The gravitational effect slows the rebound. But they don't. But when you add these two effects together, you get a zero effect. Now, if the gravity is sideways, if the gravity is downward and you're bouncing this ball off the plate sideways, then there shouldn't be any effect there either, according to classical mechanics. But in Neo-Newtonian mechanics, in one case, the gravity has to be interproducted with the jerk vector, which is the product in the case up and down. But in the sideways case, the inner product of the jerk vector and the gravitational vector vanishes. So you should get in a situation like this if you use Neo-Newtonian mechanics. And I sort of showed that you do, but the problem was I couldn't, there's very limited programming facilities in Derive, which I use, Derive 5. And so I couldn't do enough examples. I was just, to decide whether or not statistically, whether it was significant. So I was going to go on and use a different programming language, but I never got around to it. I sort of left it for another day. But we do seem to get the same sort of thing that Dmitriev measured here, whether your gravity is sideways or up and down, does make this sort of difference. And the numbers are reassuring, but as I said, I only have 50 data points, I believe, for each of the 4 cases. And so consequently, that's not statistically significant. But it's nice to know that, you know, at least you're in the right ballpark.
Yeah, he's from some fine mechanics and optics, St. Petersburg, Russia. Okay.
Yeah,
So
yeah.
Russian guy.
Yeah, he's you don't have to go to Russia or Red China, it seems, to get any experiments.
Okay, so this is a translation from a journal, some Mechanica,
Yeah,
published in June 2002. Okay,
Yeah.
or 2001, I guess. Okay, so this is a translation of an article published in a presumably peer-reviewed.
yeah. He's this guy is reputable. It's just that the Russian scientists don't have the money. They don't have $1 billion to look for dark matter or gravitational waves. You know, I mean, but he does. He's actually does a lot with what he can do. You know, with what limited resources. I mean, like that falling rotors experiment. He made a case and then he evacuated the air so the 4 rotors would be moving in roughly in a vacuum, and so